In this video, we're going to work on the ALEKS problem called drawing the Haworth projection of an aldose from its Fischer projection. This problem is going to start us off with a straight chain monosaccharide. It's going to contain either 5 or 6 carbons. This one is giving me 6 carbons, and it wants us to draw it in the cyclic form. ALEKS's drawing tool has got a nice little template that will automatically draw a 6-membered ring. Check it out right there. So you can just have that 6-membered ring drawn for you, and then you're going to need to fill in the straight line bonds on the carbon atoms of the ring, and you want to make sure that the bonds are pointing straight up and straight down. Don't angle them. ALEKS doesn't like it if you draw them at an angle. Let's fill the numbers in on this ring. 1, 2, 3. I'm only going to do 1 through 5. We'll come back to carbon number 6 later. So our job is to fill in the things that are attached to the 6 carbons of this ring, making sure that we're writing them in the correct position. By that I mean either up or down. For carbon number 1 in the cyclic version, there's going to be an OH group on carbon number 1 and also a hydrogen. And the position, up versus down, of the OH group and the hydrogen depend on whether we're drawing the alpha or beta anomer of the molecule. This problem is not specifying whether we should be drawing the alpha or beta anomer, which means that we have the option to draw the OH group either sticking up or down. It's totally our choice. I'm going to draw it up. For carbons 2, 3, and 4 of a 6-membered aldose, 2, 3, and 4 of a 6-membered aldose, the location of the OH groups on carbon 2, 3, and 4 in the cyclic version depend on the location of the OH groups of carbon 2, 3, and 4 on the straight chain version. If an OH group is on the left-hand side, it is going to end up sticking up in the ring. So for carbon number 2, because there's an OH group on the left-hand side, it is going to be in the up position on the ring. And same for our carbon number 3. The other position on carbons 2 and 3 will be the hydrogen. Anything that is on the right-hand side of the straight chain version is going to end up sticking down. So for carbon number 4, we have an OH group on the right-hand side. That means in the ring, it is going to be in the down position. For carbon number 5 and 6, this is where things get a little bit tricky. If we have the D version of the monosaccharide, which we do here, this is a D version because the OH group is on the right-hand side. If we have a D version, then carbon number 6, the CH2OH, is going to be sticking up. And in that down position of carbon number 5, there's just a hydrogen. So that's what it would look like. If we had the L version of the sugar, and the L version of the sugar, it would look like this. We'd have an OH on the left, and this would just be a hydrogen over here. If we had the L version, we would reverse the positions of the substituents on carbon number 5. So the L version would look like that. That's kind of tricky. I'm going to put it back to the way that it was so that it works for this particular problem. Now, it is also possible that ALEKS could give you just simply a 5-membered monosaccharide. So I'm just going to kind of sketch one of those out really quick, like that. Let's say that it's this CH2OH, 5-membered aldose. And if you're being asked to draw a the Haworth version of a 5-membered aldose, then you're going to want to draw a 5-membered ring. I'm going to kind of sketch that out, and there is, that looked bad, and there is a 5-membered ring down here in this drawing tool as well. Make sure that you fill in the straight line bonds. That is such an ugly looking 5-membered ring, oh my gosh. Carbon number 1 is located right here. There's 1, 2, 3, 4, and I'm going to draw carbon number 5 later. Carbon number 1, again, is going to have an OH group on it, and we're going to get to choose whether we want to point that OH group either up or down. It's going to be our choice. Carbons 2 and 3, the location of the OH groups on carbon 2 and 3 will be based on the location of the OH groups in the straight chain version. So if the OH group is on the right-hand side of the straight chain version, then it's going to be pointing down in the cyclic version, like that. And then, just like with the last one, for carbon number 4 and 5, for the last one it was carbons 5 and 6. For the last 2 carbons, we're going to draw in the position of the CH2OH based on whether it's a D or an L version of the monosaccharide. For the D version of the monosaccharide, the CH2OH sticks up, and the other thing on carbon number 4 is a hydrogen. If this was an L version, then our CH2OH would be down here, and there'd be a hydrogen up top.